Hello and welcome back to DC Circuit Fundamentals. In this module, we're going to be looking at combination circuits. Combination circuits have both series and parallel components. So we'll be looking at the basic principles involved in how to solve this. We'll be looking at 4 different circuits in this particular presentation. There are an infinite variety of combination circuits, and there's just no time to cover them all. So it's important to understand just the concepts on how to solve the different types. Once you have the basic idea, then you can solve any other or any variety of combination circuits. The last half or part of this particular presentation, we're also going to be looking at efficiency in a ladder distribution network, which is an extremely common single-phase circuit. So let's get on with it. By the end of this presentation, we should be able to look at a combination circuit, break it down into its series and parallel components, and solve for current, voltage, and power. We'll also take a look at a slightly different layout for a combination circuit, which has to do with voltage drop, line loss, and efficiency. And these are a very common type of problem, and we'll see what that looks like when we get there. So far, we've already looked at series circuits and the different principles or tenets that coincide with a series circuit. We then examined parallel circuits and did a bunch of problems for those and examined the tenets or principles around current, voltage, resistance, and power for parallel circuits. Now it's time to look at a combination circuit that has both series and parallel paths and how Ohm's law, EIR, and PEI can be used to solve for values for a combination circuit. Combination circuits have both series and parallel components. If we understand the ideas around a series circuit and the principles around a parallel circuit, then we can easily use those principles to solve a combination circuit. When it comes to a series circuit, we know that the sum of the voltages must add up to the supply voltage. Current only has one path, so we say current is common to all the series components and is the same through series components. In a purely resistive relationship, resistance adds directly, where the total resistance is the sum of the individual series resistances. Power, well, power always adds. When it comes to a parallel circuit, the tenets are just a little bit different. For a parallel circuit, voltage is common to all parallel branches, where each parallel branch has the same voltage. Notice that we're saying branches, not resistances or resistors, because it's the branch voltage that is common. When it comes to current in parallel circuits, the current coming into the node must equal the current leaving the node. We called that Kirchhoff's current law earlier. So that the total current coming to the node equals the sum of the branch currents leaving the node. When it comes to resistance in parallel, the resistance, the total resistance, is equal to the reciprocal sum of the branch resistances. And, just like series, powers always add. Power will come into play later on once we start doing AC circuits or alternating current circuits. With the complexity of an alternating circuit, If we use power, we can simplify the mathematics greatly. We have to have these two basic principles for series and parallel clearly defined by this time. You must always keep these two things separate. The series tenets must always be kept for only series relationships, because they only apply to purely series relationships. So too with the parallel tenets. These parallel concepts, principles, or ideas only apply to purely parallel relationships. You cannot mix the two. And as long as you keep these two things separate, then solving a combination circuit can be quite easy. Let's examine further. Let's start off by looking at a simple series parallel combination circuit. But first, I'm going to work just a little bit backwards so you get an idea of the process. Let's say we had a single resistor, and that resistor was 40 ohms, and it had 240 volts worth of pressure applied to it. Using Ohm's law, you could easily calculate that the current is going to be 6 amps. You may have noticed that the 40 ohm resistor, I labeled that as RT, and I also highlighted it as green. There's a reason for that. That 40 ohms is not just a single resistor. It actually turns out that it's the result of two resistors in series, a 16 ohms and a 24 ohms, which gave us a total resistance of 40 ohms. That total resistance of 40 ohms then held back the 240 volts worth of pressure to result in 6 amps of current flow. So we have two resistors in series. What do we know about series circuits? Well, one thing we know about series circuits is that current is common and resistance adds. And since the resistance adds up to be 40 ohms, the current works out to be 6 amps. And it's 6 amps through both resistors because they're in series. We know they're in series because there's only one current path. When the current comes in on line 1, it is forced to go through both R1 and RA. Since we have two resistors in series with the same current of 6 amps, we can now easily calculate the voltage across each resistor using Ohm's law, where the voltage across resistor 1 will be 96 volts, and the voltage across resistor A will result in 144 volts. Again, series circuits. What do we know? Well, resistors add directly, current is common, and the sum of the voltage drops must equal the source. So using Kirchhoff's voltage law, if we add 96 to 144, again, we get back to our source voltage of 240 volts. Again, you may have noticed that RA is highlighted green, and it's 24 ohms. That's because RA is the resultant of another combination, a parallel combination this time, where 24 ohms is a result of 60 ohms in parallel with 40 ohms. All the current comes in on line 1, and all the current has to go through R1. So R1 carries all the current, the 6 amps. Then it gets to the first node where the current can branch off, where some of the current can go through R2, and some of the current can go through R3. So since R2 and R3 have different currents than R1, they are not directly in series, because series circuits have the same current. Now if you look at R2 and R3, you can see the front of R2 and the front of R3 are tied together, and the backs of R2 and R3 are directly tied together. So R1, nothing changed from the previous circuit. So it gets the full 6 amps, and it would have 96 volts across it. R2 and R3 are directly tied together tip to tip and tail to tail. They are directly in parallel with each other. That's what allowed us to combine them together to give us 24 ohms for RA. We calculated the voltage across RA to be 144 volts. So, what do we know about parallel circuits? Well, resistance adds inversely, but parallel voltages are the same across branches. So that R2 has 144 volts and R3 also has 144 volts. Parallel branches have the same voltage. What's another tenet of parallel circuits? Well, current adds. Now that we have a voltage for R2 and a resistance for R2 and a voltage for R3 and a resistance for R3, we can calculate the current for each, where resistor 2 will have 2.4 amps and resistor 3 will receive 3.6 amps. Kirchhoff's current law says the sum of currents entering a node must equal the sum of currents leaving the node. So if we have 6 amps coming in through R1 and it reaches the node and it branches off, then the two currents in my parallel branches must also equal 6 amps. And sure enough, they do. When it comes to working out a series parallel combination circuit, one of the first things you have to do is look at the circuit and figure out what are some of the relationships. Some may become more clear than others. So how do you know where to start? Well, look for where there is only one relationship and one relationship only. Can you find a relationship that is strictly series or one that is strictly parallel? It's kind of a process where you pick away one piece at a time. And if you only change one thing at a time, keep track of your changes, then soon enough, the circuit will simplify down to something much more manageable. Your goal is to get to either a very simple series circuit or to a very simple parallel circuit. So previously I said I sort of did the process in reverse. So what would that process really look like? Well, we would start off with our initial circuit. We would then analyze it and see if we could find one relationship that was either series or parallel. So again, all the current would come in through R1, it would branch off. So R1 would have different currents than R2 and R3. When we look at R2 and R3, we see that the tips of both R2 and 3 are tied together, and the tails of R2 and 3 are directly tied together with no other resistances in between, that those two are in direct parallel. So our first step would be to simplify R2 and R3 and combine them together to an equivalent resistor, which I labeled RA. Again, subscripts are only used as place markers, so you could have easily called it RX or RY, or you could have called it R23 to signify that resistor 2 and resistor 3 were combined. It really doesn't matter, as long as you keep track of your changes. I also use a different color to keep track of my changes. Another helpful hint is when you redraw your circuit, redraw it roughly the same size and roughly the same shape, with only the thing that you are changing being the difference. That way you can clearly look between the two and easily pick out the changes. It's quite evident to see that RA came from R2 and 3, because R1 didn't change. It hasn't changed location, and it hasn't changed value, and it hasn't changed color. Now when you look at that second step, you can see that R1 is in parallel with RA. So once we have calculated out the value of RA, the equivalent resistor of 60 and 40 in parallel, we can then combine and simplify that second circuit of 16 and 24. That's a series relationship, where all the current comes in and it goes through R1, and the same current is forced through RA. So we would combine that into one equivalent resistor, or RT, where RT is equal to R1 plus RA, which gives us 40 ohms. The procedure is to simplify down to a simple series or a simple parallel. In this case, we simplified it down to one single resistor, RT. Now that we know what the total opposition equivalent is, we can now calculate IT. We have found everything for that third row. We have the voltage, the current, and the total resistance. We can now move up or back one step. Because we made the note that RT is equal to R1 plus RA, or it's a series relationship, and we look at the circuit directly above where we see it is a simple series relationship, we know that current, IT, 6 amps, is common in a series relationship. So we take the current up with us. Most of the time, as you're going through the procedure, as you're going back from the bottom towards the top, you will find something in one line that will help you find values in the line before it. What do I mean? Well, in the bottom row, we found the current. In the second row, now that we have IT, or the current, we can find the voltages for the two resistors. Now that we have the voltages for the two resistors, we can carry those voltages up with us to find the branch currents for R2 and R3. R1 didn't change from line 2 back to line 1, so all its values just get carried up. We look at RA, and we can see from the calculation of 1 over RA equals 1 over R2 plus 1 over R3 to get 24, that that's a parallel relationship. So since that's a parallel relationship, we can carry the voltage up, because we know parallel circuits have the same voltage. Now that we have the resistance and voltage for every location, we can find the two currents for the two parallel branches. Then it's just good practice to use Kirchhoff's voltage law, or in this case, in line 1, Kirchhoff's current law, to see if the currents add up to the incoming current to the branch circuit, which it does. So let's sort of review the procedure using the same circuit. We'll call these the guidelines for solving series parallel combination circuits. The first thing that you should do is try and find your RT by identifying series and parallel relationships and changing one thing at a time. You are encouraged to only change one relationship at a time, either a series relationship or a parallel relationship. Redraw your circuit. That helps you keep track of your changes. This is a very simple circuit, but you may have one that you will have to redraw 5 or 6 times. So if you keep track of all your changes, it makes it that much easier to find all your values and remember what you did. Space your work out. Give yourself room to work back. As you redraw your circuit, give yourself a little bit of room so that you can put all the calculations associated with that step close to or near that step. If you keep track of all of your changes or steps, then it's much easier to work your way back. Complete each section as you go through. So as you solve your way down to get your RT, calculate everything you need in the simplest form. That bottom circuit just had one voltage and one resistance, so it was easy to find one current. When you work back one step to row 2, the only thing you had to find there were the 2 voltages. You would then carry the voltages back up to step 1, at which point you had all the voltages, and all you had to do was find the 2 branch currents. You should check your work at each step. And once you're done, you can use Kirchhoff's voltage law or Kirchhoff's current law to do a final check. Even the most complex circuit, you can use Kirchhoff's voltage law, which says the voltages along any one current path must add up to the source. So if you take one complete current path from start to finish and add up all the voltages, you have to reach back to the source voltage. Another tip that also can help is to make your drawings the same size or similar size and similar shape. You can see here in my drawings that they're roughly all the same size. The changes are directly underneath the things that were changed. I personally also use colors to identify changes. Some people find using colors help to process the information, so that when you look at this particular layout, anything that is in blue is a voltage. In these combination circuits, anything that is green is something that has been combined or changed or is an equivalent resistance. Reds are used for current. So that if I see something that is red, I know automatically that that is a current or a current calculation. Blue is a voltage or a voltage calculation. And greens indicate a change in something. You may have seen me use green in the past for power. Let's do another problem together. We'll use the same shape, but we'll use different values this time. So here we have a series parallel combo circuit with 600 volts. Again, we would analyze the circuit. All the current would come in and go through R1. Then it would reach a node where some of the current can branch off and go to 2, and some of the current can branch off and go to 3. Then after 2 and 3, all the current will come back together again. So R1 is sort of in series with 2 because some of resistance 2 current comes from 1, but some of resistance 3 current comes from 1. So they're not directly in series because they do not have the same current. Visualizing how the current flows in a circuit will help you analyze the relationships. So we would avoid doing anything with R1 to start with. We would then look at R2 and R3 and say, well, are they in series or parallel? Well, different currents, so they're not in series. But are the tips tied together and are the tails tied together, the front and the back? Are they directly across from each other? Well, they are. So then they're in parallel. So identifying R2 and 3 in parallel we could then combine them to make an equivalent resistance. Again, I call my first change RA, where RA is R2 and R3 in parallel, which gives us a resultant of 60 ohms. We would then ignore the first circuit and only work with the second. Now we can analyze it to simplify it. Now we have R1 and RA in series. You can clearly see or try to visualize the current coming in from the start of the circuit, and how all the current going through R1 must also go through RA. There is no other place for the current to go. So those two resistors must be in series. So now we can combine those two resistors to get an equivalent resistance. That'll leave us with just one, RT. I called it RT because it's the total. There's nothing else left. RT comes from R1 and RA in series, which gives us 100 ohms. Since we have 600 volts, that's going to give us a current of 6 amps. Now we can work our way back. And if we only made one change at a time, it's quite easy to only do or perform one set of calculations at a time. RT came from R1 and RA in series, so series circuits have the same current. Now that we know that these two circuits have the same current, we can work out the two voltages for each, where V1 is 240 and VA is 360. At this time, we would do a check and say, it's a series circuit, and what do I know about series circuits? Well, current's common, resistances add, and voltages add. We would use Kirchhoff's voltage law to see that those two resistances add up to the source voltage. And they do. Now that we have a current, a resistance, and a voltage for all locations in step 2, we can then move back up to step 1. In the drawings, you can clearly see that RA is a change from the previous step. Because of our note and because of how it's laid out, it's very easy to see that RA came from R2 and R3 in parallel. And what do we know about parallel circuits? Well, voltage is common. So each of those resistors will get 360 volts. R1 didn't change from line 1 to line 2. So its values did not change. It still has 6 amps and 240 volts. But the current branches off into R2 and R3. But now that we have a resistance and a voltage for each, we can now calculate the current for each, where R2 will get 4 amps and R3 will get 2 amps. We had 6 amps total coming in, so we should perform a Kirchhoff's current law to see that 4 and 2 do add up to IT, which they do. This is the basic procedure for going through a series parallel combination circuit, where you simplify one relationship at a time to get to an RT, keeping track of each change as you go. Then, once you get to an RT and an ET, you can find your total current, IT. Then, you can alternate working your way back through the steps, solving steps completely as you go through. So let's carry on. Let's try something else. Let's take a look at a circuit that's a little more involved. Now you may look at this circuit and think, oh my, that's a lot more than we were doing before. And you'd be right, there are more steps involved. But the process is exactly the same. Find a single relationship that is either series or strictly parallel, and then simplify. Your goal is that you want to get to a simple series or a simple parallel circuit. If everything is not one relationship, don't change it. So let's carry on. If you think about the current coming in through line 1, all the current is going to go through R1, but then it's going to branch off and go through R2 and R3. So R1 does not have the same current as 2 and 3. But then all the current comes back together and is forced through R4. Now you might think, well, if R4 has all the current, then it's in series with R1. And you'd be correct, but there's something in between. And since there's something in between, you're better off leaving it alone. Then all the current is going to, after it goes through R4, is going to break up 3 ways. Some of it's going to go through R6, some of it's going to go through R7, and some of it's going to go through R8. And then it's all going to come back together again and leave through line 2. So you have 2 places you could start here. R1 does not have the same current as 2 and 3. But when you examine 2 and 3, it's very similar to the one we did before, where the tip of R2 is tied to the tip of R3. And the tail of R2 is tied to the tail of R3. 2 and 3 are directly in parallel with each other. So you can start there, where you can make R2 and R3 an equivalent resistor, where RA is equal to 24 and 48 in parallel, which will give you a resultant of 16 ohms. Now you can analyze this circuit, the second one, where we've got R1 and RA and R4. You can clearly see that those are in parallel, but series, my bad. R1, RA, and R4 are in series. But then the current breaks up 3 ways between 6, 7, and 8. If we combine 6, 7, and 8, we'll end up with an equivalent resistance again. And then we'll simply have 4 resistors in series. And that is your best option. So let's combine 6, 7, and 8, which are clearly across from each other, and combine them into what we'll call RB, where RB is R6, R7, and R8 in parallel, which gives us a resultant of 12 ohms. Now in our third drawing, it's quite easy to see that those 4 resistors are in series. And now is a good time to combine them in series. So if we take those 4 resistors and put them together to make one equivalent resistor, we will end up with 75 ohms. Now that we have RT, ET, we can easily get IT. And yet again, it has turned out to be 6 amps. Now you might be able to see why we didn't combine 1, RA, and 4 in step 2. Because it's much easier in this step, where we have 4 resistors in series, to deal with series voltages. Because series currents are the same, so we can easily, in this step, calculate out the 4 voltages. Where R1 is going to get 150 volts, RA is going to get 96 volts, R4 is going to get 132 volts, and VB is going to be 72 volts. And sure enough, when we add those together with Kirchhoff's voltage law, we end up with 225 volts. You'll notice that I only labeled VA and VB on my circuit. And that was just to save a lot of clutter. But what do we know about VA and VB? Well, if you look directly above, RA came from a parallel combination, and RB came from another parallel combination. So that means RB and its parallel branches of 6, 7, and 8, they each get 72 volts. And with parallel branches having the same voltage, we can then calculate the current through each branch. So that R6 gets 1.2 amps, R7 gets 0.8 amps, R8 gets 4 amps, and when we add up those 3 branches together, we get back to our 6 amps. Now that we've found all that we can find for step 2, we can move back one step. And again, our A, that has 96 volts, came from a parallel branch of R2 and R3. So those branches have 96 volts, which then allows us to calculate the current in each of those branches, where we'll get 4 amps in resistor 2 and 2 amps in resistor 3. And sure enough, Kirchhoff's voltage law says 6 amps are coming in, that my branch currents must also equal up to 6 amps. We can now fill in all the values for all our unknowns. And by the time we get all done, we have all the values for all the different resistors, all the currents, and all the voltages. If you organize your work clearly and keep all your values together, then it's very easy to organize and pick out the answers that you need. Here's a simple 2-loop ladder diagram. We call them a ladder diagram because if you were to rotate it 90 degrees, it would sort of look like a ladder with 2 rails running up with horizontal rungs cutting across. These are probably the most common circuit in real application, and we'll look at why that is in a little bit. If we apply our rules of series parallel to this, where we're looking for only one relationship, and if we're unclear of the relationship, then we should avoid it. So here we have a source voltage of 360 volts. I'm going to make my loops, or I'm going to take my current thought in a clockwise rotation, which means my current's going to leave from the 360 volt source and head towards R1 of 8 ohms. So R1's going to get all the current. The current is then going to get to the first node, where it can branch off, where some of the current can go through R3 and then the rest of the current can go through R4. So R1 does not have the same current as 3 or 4. Now if I keep following through 3, I can see it reaches another node where currents are going to do something again. So I'm just going to leave R3 for now. Let's take a look at the current through R4. You can see that the current as it passes through R4 has no other place to go but through R5. And it is also the same current that is forced through R6. And then it reaches another node, where it would meet up with the current from R3. So the simplest place to start would be R4, 5, and 6, because we can easily see that those 3 have the same current. So we would simplify 4, 5, and 6 together to give us an equivalent resistance, which I labeled as RA. And when we add 47, 33, and 40 together, we end up with 120 ohms for our equivalent RA. Now we can ignore the first step and just focus in on the second step and simplify it. If we do the current analysis again, the current is going to leave my source and head towards R1. And then we'll reach the first node, where some of the current will go through 3 and some of the current will go through RA. Then the current will come back together again after R3 and after RA. R3 and RA are directly in parallel. So we would then simplify them. to give us another equivalent resistance, which I will label as RB because it's the second one. Now RB is equal to R3 and RA in parallel, or 180 in parallel with 120, which will give us an equivalent of 72 ohms. Now that we've simplified the second circuit for the third circuit, we can now look at the third circuit and simplify it. It's very easy to see now that these three resistors, R1, RB, and R2, are all in series. So we could make an equivalent total resistance of those three in series, where RT is simply 8, 72, and 10 together to give us a total of 90 ohms. We have an ET of 360 and RT of 90 ohms. That means we'll have an IT, or a total current, of 4 amps. We now have all the values for our fourth circuit. So we can move up one. A lot of times, not every time, when you find one identity on one step, you'll be finding the other in the next. What do I mean? Well, we just found 4 amps worth of current in our fourth step. Now, not always, but the majority of the time, we'll be finding voltage on the step before. So we found 4 amps. That 4 amps in our series circuit of step 3 will now help us find the voltages for each of those series components. And sure enough, we get V1 of 32, VB of 288, and V2 of 40 volts. When we apply Kirchhoff's voltage law to that, we end back up with our 360 volts for our source. Now looking at our drawings and looking at our color changes, we can see that RB, as well as our note, RB came from RA and R3 in series, parallel. So when we go back and look at those two things in parallel, and RB has 288 volts, then R3 and RA must also have 288 volts because they're in parallel. And parallel branches have the same voltage. We can now calculate the current in each of those branches, where IA is 2.4 volts and I3 is 1.6. And when we add those two together, we end up back with our 4 amps for IT. Now that we have IA of 2.4 amps, and we know that RA came from a series combination of 4, 5, and 6, we can find the voltages for 4, 5, and 6. And that adds back up to our parallel voltage of 288 volts. We can now go back to our different steps and gather all the information that we had before. All our currents, all our voltages. They're all there. Why don't you try this one on your own and see if you can get through it? I'll give you 2 minutes. If you need more time, maybe you can pause the video here to see if you can get through it. Here there's 120 volts applied. R1 is 4 ohms. R2 is 6. R3 is 50. R4 is 8. R5 is 60. And R6 is 7 ohms each. How are you getting along with that? Once you identify certain patterns, it gets easier. Such as once you identify that this is a ladder circuit, you know immediately to start at the back end. So in this case, simplify 4, 5, and 6 to give you an equivalent resistance of RA. RA comes from 8, 60, and 7 in series together, which gives you 75 ohms. Now you can put R3 and RA together in parallel to give you an equivalent RB, where RB is equal to 50 and 75 in parallel, which gives you 30 ohms. You can now combine 4, 6, and 30 to give you an RT of 40 ohms. Now you can start working your way back. That's going to give you a total current of 3 amps. You carry your 3 amps back one step, calculate out your 3 voltages for R1, RB, and R2. RB gets 90 volts. It came from a parallel equivalent, so each of those parallel branches gets the same voltage. You can now calculate each of the currents for those 2 branches. You carry the current from RA back up into the back branch of R4, 5, and 6 because they're in series, which allows you to calculate the 3 voltages for the 3 resistors in the back. It's always good practice to check your work as you go along. And then you can gather all your values and fill them in. And you can also perform Kirchhoff's current law to make sure that as your IT of 3 amps comes along and reaches the first node, when it branches off to R3 and R4, that those 2 currents of 1.8 and 1.2 add back up to your IT of 3, which it does in this case. So I hope you get or have a better understanding of the process. Simplify down to an RT. Keep track of your changes. 1 change at a time. Use values that you calculate in one of your simple circuits to move back one step and find values or unknowns in the circuit before. Follow these simple rules and it works out to be pretty easy because all you're doing is EIR. Let's look at a more practical application. Here we have a standard North American 120 volt receptacle where it's fed by 2 wires, line 1 and line 2N. The N would stand for neutral if it was a 3-wire system. But in this case, it's the return wire, so it's more appropriate to call it line 2, where all of my current or my feed comes in on line 1. And then if I was drawing any current, it would return back on line 2, or the blue wire. This type of problem looks more at line losses, because if I have a piece of wire, depending on the length of the wire, that wire is going to have some resistance. The longer the wire, the more resistance my feeder wires are going to have. And the more impact that those feeder wire resistances will have on my output load, or whatever it is that I'm plugging into the receptacle. We'll be looking at some sort of generic load, something to plug into the receptacle. A load is usually something that either draws current in amps or wants to dissipate energy in watts. P, power, watts. For this example, let's take a little unit heater. Our little unit heater here is going to want to draw 12 amps. It could be any sort of generic load. Really doesn't matter. So once we plug our unit heater in, that's our load, the unit heater, then it's going to start drawing 12 amps. Now my input source voltage is 120 volts. My current through my feeder wires, 12 amps, across 0.2 ohms, is going to use a little bit of voltage. We can represent this diagram by a simpler schematic. So here we have a source voltage of 120 volts, which is a standard North American residential voltage. Our wires, we're going to represent those, our feeder wires, by two resistors, R1 and R2. And they're going to have a very insignificant resistance of 0.2 ohms. Again, the further away my receptacle is from my source, my panel, the more resistance those wires are going to have. The cylinder on the end, labeled load 1, well, that's just any sort of generic load, whatever that is. Again, in our example, we're going to use a unit heater. And again, it's just a series circuit. So that when we plug our unit heater in, the current only has one path to follow. So my 12 amps will flow through my series circuit of R1, R2, and my load. Let's examine this circuit in a little bit more detail and calculate out some values based on the numbers we have. So here we have our simple circuit again, where we have two feeders, R1 and R2, feeding a load. And again, for simplicity, we'll plug in our little unit heater, and it's going to draw 12 amps. Now, in the previous problems, we went about by solving through resistance. But in these problems, what we really care about are voltages, currents, and powers. We're not really concerned about solving for the load resistance. It's just not important. All we really care about with the load is how much current or how much power it's consuming. And again, in this particular example, our load is going to draw 12 amps. Since our load's drawing 12 amps and our feeder wires, R1 and R2, each have 0.2 ohms, we can calculate the voltage out for those two lines, where each of them are going to have a 2.4 volt drop. We call this the voltage drop. This is the voltage that is dropped by the lines that are feeding the load. It's a series circuit. So we can now calculate the voltage to the load, where the voltage of the load is equal to our source, subtract our voltage drop, which in this case is 120 take away 4.8 volts, for a total of 115.2 volts. This is one of the things we have to consider as electricians, is how much voltage are my feeder wires going to drop before I can actually use it at my load. We then have to compensate the size of the wires to reduce the resistance of the wires so that we reduce the voltage drop to maximize the voltage at the load. You have to consider the current or power of the load, because the more current a line draws, the larger the voltage drop on those lines. Let's carry on. Now that we have the voltage to the load, we can calculate all the powers for the circuit. The source voltage of 120 volts has to supply 12 amps. So the source that has a total circuit power of 1440 watts. The load power can be calculated from the load voltage multiplied by the current, which in this case gives us 1382.4 watts. How much power is coming in from the source, 1440, is different from how much power our load is actually dissipating, 1382.4. That's because our feeder wires are actually going to heat up. Because it's a resistance and because current is flowing through that resistance, those wires are actually going to generate a little bit of heat. We call that the line loss, or line loss power. That's the difference between how much our source is putting in and how much our load is actually able to dissipate. That's also the reason why we have to be careful when we're installing wires, such as putting wires in conduit. If we put too many wires in conduit, then each of those wires is acting like a little heater, and they're going to generate heat or dissipate power. You have to compensate or allow that heat to escape. You have to manage that heat, if you wish. We could also calculate how much heat or power is being dissipated in the wires by simply multiplying the current through the wire by the voltage drop of the wire. In this case, each wire is going to dissipate 28.8 watts for the total of the 57.6 watts of line loss. Now that we have all the powers, we can actually calculate the efficiency of this circuit. We use the Greek letter eta here to represent efficiency, where efficiency is equal to the power at the load, or the output power over the total input power. Multiply that by 100, and this circuit works out to be about 96% efficient. The power that is dissipated or lost in the wires is energy that we do not want to lose. That's why we call it a loss. We cannot avoid line loss power. Let's take a look at another example with different numbers, shall we? Here's another circuit similar to what we just did. But this time, maybe the wires are a different length. So they're only 0.818 ohms each, or 180 milliohms if you wish. Let's hook this up to a 220 volt source this time. And it's a different unit heater. So let's say it's drawing 20 amps current this time. Let's calculate all the voltage drops, the voltage to the load, the input power, the output power, the line loss power, and the efficiency. Well, we start off one of these problems. Since we have a current and a resistance, we can calculate the voltage drops on each line, which will give us 3.6 volts per line, for a total voltage drop of 7.2 volts. Again, if you look at the circuit and follow the current through, you'll see that it's a series circuit, where the total voltage is going to equal both the voltage drops and the load voltage. So if we want the load voltage, all we have to do is take our source, subtract the drop, and we'll end up with the load voltage, which in this case is 212.8 volts. Now that we have a load voltage, we can calculate all the powers. Total circuit power, ETIT, well, it's going to give us 4.4 kilowatts. The load power, or the output power, well, just multiply the voltage by the current, and that'll give us 4,256 watts. The difference between those two will be our line loss, which gives us 144 watts dissipated by our two wires together, which means that each wire is going to dissipate 72 watts individually. Now that we have our input power and our output power, we can calculate our efficiency. Efficiency is equal to power out over power in, multiplied by 100%. And this circuit as well is running around 96%, but 96.72% to be precise. Again, these are a more practical problem where we're actually looking at our voltage drop due to our wire resistance, the line losses due to the wires or feeder wires dissipating heat, and then how that all impacts our output voltage and power. It's not very often we have a single receptacle wired up by itself. In most residential and commercial applications, we have multiple receptacles wired in parallel, one after another. In this example, let's say load 1 is drawing 8 amps and load 2 is drawing 6 amps. We can represent this circuit by this schematic diagram. And as you follow the arrows around and envision the current running through it, it does act like a parallel circuit, where the 8 amps of load 1 is going to meet up with the 6 amps of load 2 to give us a total of 14 amps for our total current. The problem arises when we take the resistance of the feeder wires into consideration. In this example, the wires running out to the first load have about 0.1 ohms. And then the wires that run to feed load 2 from load 1, well, they must be a little bit longer in this example because they're 0.2 ohms. And it's because of these resistances of the wires, our feeder wires, that we lose voltage to our loads. So let's take a look at this circuit in a little bit better detail. Let's look at the voltages to the loads and then how the powers are distributed throughout this circuit. So again, as we envision the current, we can see that this is a series parallel combination. And again, the branch currents through Kirchhoff's current law have to add up, where the load 1 current of 8 amps meets up with the load 2 current of 6 amps to give us a total current of 14 amps in our first loop. So our source has to supply 14 amps. The first feeder wires of 0.1 ohms are going to have a total of 14 amps flowing through them, which means that they're going to have a voltage drop of 1.4 volts each, or a total voltage drop on loop 1 for 2.8 volts. If we apply Kirchhoff's voltage law, sum of currents around any one voltage loop must add up to the source. We can use the source voltage and the voltage drop to solve for the load voltage of 1. Resistor 1 is going to drop 1.4 volts. Resistor 2 is going to drop 1.4 volts. And when we subtract that from 120, we end up with 117.2 volts for load 1. As we move further down the line through resistors 3 and 4, each of those is going to have a voltage drop of 1.2 volts. Now, if we wanted to calculate the voltage to load 2, you have a couple of options. You could start off with your source voltage and subtract V1, V2, V3, and V4 in order to get load 2. But we've already subtracted V1 and V2 from E to get the voltage at load 1. So if we want the voltage at load 2, all we have to do is take load 1's voltage and subtract the voltage drop on the second loop. So if we take the 117.2 and subtract our 2.4, we end up with a load voltage of 114.8 volts. This is standard across all ladder loops. You may have recognized that this is a ladder network, but we're not concerned about the load resistances. We only really care about the load current and the load voltage. As you add more loads in parallel down a line, due to the line losses or the voltage drops, your voltage to your loads reduces. We can calculate the total source power, PT. And in this case, it comes out to 1.68 kilowatts. We can calculate the voltage to load 1. Take voltage load 1 times the current of load 1, and we end up with 937.6 watts. Do the same for the second load, and we end up with 688.8 watts. Always be careful and make sure you use the correct voltage and the correct current for each load. Now that we have the two load voltages, we can calculate the total load power by adding the sum of the two individual loads. And in this case, we come up with 1626.4. So now we have the total input power, we have the total load power, and the difference between those two will be our line loss power, which in this case works out to be 144 watts. You could, as before, calculate each of the individual line powers of R1, R2, R3, and R4, add them together, and you should come back to 144 watts. Now that we got our total input power and our total output power, and accounted for our losses, we can calculate the efficiency of this circuit, where our percent efficiency is equal to our total output power over our total input power. And again, in this example, it works out to be 96.81%. Let's take a look at this second circuit. This time, load 1 is 15 amps and load 2 is 20 amps. Our feeder wires have changed, so their resistances have changed. And this time, let's hook it up to a 220 volt source. Applying Kirchhoff's current law, where load 1 is 15 amps and load 2 is 20 amps, we're going to have a total current of 35 amps. That means our source has to supply 35 amps, which means our first feeder wires of R1 and R2 have to support the entire load current. We can now calculate the voltage drops on those feeder wires in the first loop. which gives us 7.7 volts each for a total voltage drop of 15.4 volts. Having that calculated, we can now figure out what the load voltage would be. If we take our source, about 220, subtract our voltage drop of 15.4, our load 1 will only get 204.6 volts. Calculating out the voltage drop in the second loop, we get 3 volts on each line for a total voltage drop of 6 volts. Taking our load voltage of 204.6 and subtracting 6 volts, we end up with a second load voltage of 198.6. Our total source power is ETIT as always, and we end up with 7.7 kilowatts. Keeping in mind that if we're calculating our loads, we have to use the load voltage and the load current for each respective load in order to calculate the power in that load. Where load 1 is 3069 watts and load 2 is going to dissipate 3972 watts for a total load power of 7041 watts. Now that we have our total input power and our total output load power, we can calculate the losses of the heat that is going to be generated in our wires. And in this case, all of our wires together are going to generate 659 watts, which is a significant amount of heat. Having our total input power and our total output power, we can calculate our efficiency for this circuit, which in this case works out to be 91.44%. You will notice that as currents go up, your efficiencies go down. So in review, when calculating or analyzing any combination circuit, you really have to have the basic ideas or tenets for each of the different circuits. Series circuits, voltages add, currents are common, resistances add directly, and powers always add. For a parallel circuit, voltage is common, but currents add. Resistances is the reciprocal sum of each branch resistance. And again, powers always add. When solving for a simple resistive network, find your way through to RT. Change only one relationship per step, either a series relationship or a parallel relationship. Draw out each step. Keep track of your steps. Give yourself plenty of room to work back. Complete each section as you go through it. This will help you to keep track and actually help you to be more accurate in your assessment. I hope these tips and tricks and these guidelines help you to figure out many different types of combination circuits. Finally, in conclusion, let's take a look at some guidelines for solving some parallel power problems. The first thing you should do is solve for all your currents. Use Kirchhoff's current law to solve. As we did in this example, 8 amps and 6 amps gave us 14 amps total. Once you have all your currents in place, then solve for all your voltages. find your voltage drops, and then find your voltages to the load. Now that you've got current and voltages, solve all your powers. Finally, once you have all the powers, you can find your circuit efficiency. This concludes a presentation on combination circuits.